Oh, okay.
Yeah, thanks for the chance to come in and talk to you about nuclear physics in core collapse supernovae. So the gist is that core collapse supernovae mark the end of the line of stellar evolution and also the beginning of the high energy astrophysics universe. And it really only lasts a couple of seconds. So it's a really exciting time in the life of a star. And it's critical, nuclear physics is critical because these environments have such extreme conditions. And so we really need to have nuclear physics input in order to study these extreme systems. But at the same time, they, astrophysically speaking, they're a great laboratory for learning about the same nuclear physics that we're trying to learn on Earth. And the gist of my talk, I think the point I kind of want to get across is that we're really now, I think, at a turning point when it comes to core collapse supernova theory. We have state-of-the-art progenitors, and when we use modern tools and neutrino and nuclear theory, we can reproduce observations of core collapse supernovae. So this is something we couldn't have said, 10 years ago, for sure. Supernova have a broad connection to the universe, and I think I'm just going to skip over this. But really, I mean, they're connected to many parts of the universe and to many parts of nuclear physics as well. What core collapse is, as I said, the death of a massive star. It starts when the iron core formed during stellar evolution becomes unstable. The electron degeneracy pressure can no longer support it, and it collapses. The core collapses. In the process, ultimately, a huge amount of energy is released, something like 300 times 10 to the 51 ergs, or 300 beta. Most of that gets radiated in neutrinos, the predominant way for energy to escape. Some of it goes into the explosion, exploding the rest of the star and giving us the supernova that we see. Nuclear physics really plays an important role even during this collapse, when the core becomes unstable and collapses. This is a chart of the nuclides. Highlighted in different colors are nuclei that contribute to the deleptonization of the core as it collapses. So these are nuclei that capture electrons and emit a neutrino and reduce the electron degeneracy pressure during collapse and accelerate the collapse. And really there's this region here, this diamond region, which are the nuclei, 74 nuclei that contribute most to the physics during the collapse. And this is a sentence from this paper here. Variations in key characteristics of the supernova, things we care about when we're modeling supernova, have variations of order 50% just due to uncertainties in the electron capture rates on these 74 nuclei. So these 74 nuclei are really important nuclei to study, and is a big place in core collapse theory where nuclear physics can help. So that was the collapse phase when the core is collapsing. It collapses all the way to nuclear densities when the nuclear force can support the star against collapse. So the nuclear pressure can create a stable object, a protoneutron star, that launches a shock, and the shock wave propagates out. It dissociates the nuclei that are outside the shock, so the iron group nuclei, into neutrons or protons, and it heats up the material. The hot material emits neutrinos, and these two reasons are why the supernova shock stalls. And the goal of supernova theory has been to understand how we can re-energize that shock. And the prevailing mechanism is the turbulence-aided neutrino mechanism. This is where neutrinos from the blue region, the cooling region, are emitted, travel outwards, and heat the red region. They drive convection, create turbulence, and this turbulence and also the heating help support the shock and push it out and cause an explosion in many cases. And this is, as I mentioned, proven successful in many models. Here's 11 out of 14 models that are successful from the Princeton group. These are state-of-the-art simulations, symmetry-free, full three-dimensional simulations here with many progenitors. This is another recent simulation, a full 7 seconds after the core reaches nuclear densities. Also a successful explosion with no symmetries and a modern, fully modern neutrino and nuclear physics. And in this particular case, after 7 seconds, they reach the canonical energies that we observe in core collapse supernovae, so of order of beta. So this is kind of, no longer can we say that supernova simulations don't explode, or they don't explode or they explode but don't reach the canonical energy. I think this is why I say we're kind of at a turning point now. The reason why, along with having full 3-dimensional simulations of core collapse supernova with modern physics, neutrino and nuclear physics, also important, and for example, important in that last simulation from the Garchian group there, was using multi-dimensional progenitors as well. So modeling progenitors in the final stages of stellar evolution to capture the multi-dimensional dynamics. This is a paper from this year from Carl Fields, where here what you see is a MESA model, so a 1-dimensional model. But they've simulated it the last 7 minutes in 2D and in 3D. So this is what it looks like in 2D. This is what it looks like in 3D. What you're seeing is the convective velocities. Yellow colors are large convective velocities. Here, much larger convective velocities than in the 1D model. So this is kind of the takeaway from this and many other studies that are looking at pre-supernova evolution not in spherical symmetry. And this large convective velocities and perturbations in general in the progenitor model play a really important role in the core collapse itself. So they induce turbulence and convection, which is helpful for the explosion. And they also give over densities and under densities of the accreting material, which also helps trigger the explosion. So next, I want to talk a little bit about the equation of state, which is also critical for core collapse supernova simulations, because it sets the pressure of the material and everywhere inside the shock, essentially. And recent efforts have really demonstrated that a very important aspect of the equation of state is the thermal dependence. And so this was mentioned in the last talk. In supernova, we get temperatures up to 50 MeV is completely realistic. And if you're talking about black hole formation, it can go even higher than that. And this thermal dependence, it's harder to constrain from theory and from experiment, but it's really key for supernova. So this is several 3-dimensional simulations where the effective mass is varied, and the effective mass gives different thermal pressures in the core collapse environment, and this is more conducive to explosions when you have a high effective mass in this parameterization that's used here. So thermal dependence of the equation of state is really important. Okay, so this is my summary slide that I have here. I think some recent accomplishments really are that, like I said, prior to 10 years ago, now we have success in achieving explosions and reproducing observations. This is in part due to more realistic neutrino interactions and nuclear equations of state. I think this plays a big role, but then also this turbulence and convection, both what you see in multidimensional simulations, but also what we have from the pre-explosion or the pre-supernova phase. Another, I think, recent accomplishment is really this, and I know we were told not to put our own stuff here, but this is not really my work, but it's really the community's work. So there's a huge number of authors on this paper where we really, where we really tried to actually simulate the same thing. And when we do this, we see excellent agreement between all the codes. So hopefully, I think this convinces us, like our community, but also everyone here, the broader community, that when we simulate supernovae, we are doing a good job, and we're able to, we're not all getting random different results. I think we're doing a good job. And I think another recent accomplishment, I think it was the last JINA town hall meeting where Chris said, Chris Sullivan really wanted to find out what nuclei are important for electron capture in the core collapse phase. So I think that was a recent accomplishment as well, all the work that the group there in MSU has done. And then future directions, just quickly, I think maybe the one future direction will be, how do we explain the supernova that neutrino mechanism can explain? So large explosion energies, large nickel masses. I think this is a big direction in the future, and maybe it involves some interesting nuclear physics, or maybe not, we'll see.